so 6.1, number 7. Alright, so it says sketch the region bounded by the graphs of the equation and find its area. So we have y equals x squared plus 1 and y equals 5. Alright, so first thing we're going to do is graph it. So if we graph this, just throwing a graph on there. That's going to be your basic parabola moved up 1. So it'll look something like that. And then y equals 5 is the line going there. So the region that we're talking about is this region here. Okay. And so what we're trying to do is we're trying to find the area. The first thing we need to figure out, is this an r sub x region or an r sub y region? In other words, are your boundaries going to come off of x or are they going to come off of y? It's going to be an r sub x. Now, it could be an r sub y if you want to go that way. It's going to be a little more difficult, but I would definitely say that it is an r sub x region. So our goal here to find area is going to be the interval. This is kind of straight off your formulas page. A to b of f of x minus g of x dx. Alright, so there's your formula. So, since this is an r sub x region, we are going to use x boundaries. Now, to find the x boundaries, you can either set these equal to each other. If you plug 5 in for y, you'll have 5 equals x squared plus 1. And then you have 0 is equal to x squared minus 4. So we know that x is going to be plus or minus 2. So there's your boundaries. So the area is going to be equal to the integral from -2 to +2. And if you want to use symmetry, you can. But if you use symmetry, make sure you do 2 times and then go from 0 to 2. So if you want to do symmetry, that's fine. Okay. So then what we're going to do is we're going to take, since it's an r sub x region, we're going to do your top function, which is going to be your 5, y equals 5, minus your bottom, which is actually going to be your parabola, so that's going to be x squared plus 1. Clean it up a little bit. And we'll have what? Negative x squared plus 4. So far, so good. Okay. So then all we have to do is integrate this. So if we integrate it, we're going to have negative x to the third over 3 plus 4x integrated from -2 to 2. And again, like I said, if you use symmetry, it'd be 2 times that integrated from 0 to 2. Completely and totally your choice. Okay, so if we plug in, we're going to have -2 cubed, which is going to be -8/3 plus 8 minus, plug the -2 in, that's going to be what, 8/3 minus 8. Okay, so now if you plug this in your calculator and you distribute that negative sign, basically what you have is -8/3 plus 8 minus 8/3 plus 8. So you can see that it's not going to go to 0. They're not opposites, which is what some people are, if you get 0, you're thinking that it is going to be opposites. But the signs work out to where instead of having opposites, you're actually going to be doubling it, which is if you use symmetry, where this is where the 2 comes from play. So I think if you plug that into your calculator, you should come up with 32/3. Anything else?
Could you go over again when you have the, when you set it equal to 0 and 0 equals x squared minus 4?
Uh-huh.
You separate the x. What would be there?
Well, to find my boundaries, what I did was I took these two, and since you have y equals x squared plus 1 and y equals 5, I can say y equals y. And so what I did was I said x squared plus 1 is equal to 5 since y is equal to y. And then if you minus 5, you're going to get x squared equals negative 4. Now from here, you're just going to factor because that's the difference of two squares.
Okay.
And so when you set them equal to 0, you get negative 2 and positive 2. And those are just your boundaries. Anything else? You don't ever have to use it. You can use it if your boundaries, for example, if your boundaries go from a negative to a positive of the same number. So if your numbers go from negative a to positive a, you can use symmetry there. But now if they go to like from negative 1 to 2, you can't do it there.
Only if they're the same on both sides of the same cross.
Yeah, as long as your boundaries are opposites, yes, and your functions are the same. Yeah. If your function is symmetrical, then your boundaries are symmetrical, then you can use symmetry. Anything else? Okay. Well, you have a test Monday, and that test, as promised, will cover 6.1, 6.2, 6.3. And then, remember I asked you to go back and look at those review slides that we did from Cal 1 and before. So there will be a little bit of Cal 1 on there, just basic differentiation and integration and so on and so forth. So for your test on Monday, make sure, of course, that you have your Chapter 6 formula page printed out because you will be able to use that on your test. And then make sure you have your Cal 1 formula page that we gave you in Cal 1. And if you don't have either of those, you can find them on Blackboard. And then if you want to, I don't think you'll need it much, but if you want to print out your trig identities page, you can. Like I said, I don't think that you'll need it that much, but if you feel that you need it, go ahead. Now, as far as knowing your radian equivalencies, I told you I put a unit circle and I didn't do it. But the ones that you'll need are in the back of the book. So if on the back of your Cal 1 sheet, if you want to copy that table that's in the back of the book, you can. Okay, and you know which one I'm talking about, yes? On the back inside cover of your book, there's a table that says special values of trigonometric functions, when it gives you degrees, radian, sine, cosine, tangent, cotangent, secant, and cosecant. You can copy that on the back of your trig identities or your Cal 1 sheet, either way. So you'll have that at your fingertips also. But in the end, you're going to be using your calculator anyway, I want to finish through 6.3. And then, of course, we will go into a little bit of 6.5. But again, your test next week will cover 6.1 through 6.3, and you will be responsible for the suggested homework problems for bonus points. I mean, it's not mandatory, it's not a grade, it's just purely bonus points if you choose to do them. So that's completely and totally your choice. As I told you before, your test will come from any slide, any problem that we did in class, and off of the suggested homework problems. Okay, so if you want to study thoroughly for your test, that's what you need to look at. You need to look at the PowerPoint slides that we've done in class, and you also need to look at 6.1 through 6.3 suggested homework problems. Okay. If you need any help next week, during class, I will only devote 15 or 20 minutes going over those homework problems. So if you think you'll need additional help beyond that, you need to come see me before class in my office, okay? Because I'm not going to use all class time to do that. And then I'll go into 6.5 just a little bit, and then I will give you at least an hour and a half to take your test, okay? All right. So last week we left off with doing the disc washer method. Some things that I want to reiterate on your formulas page. Hopefully you have that out. Now when you start working on the suggested homework problems, it does not say use the disc method or use the washer method. You have to figure out, am I looking at a disc or am I looking at a washer? And depending on the graph, depends on which one of these you're going to use. On the test, I will say use the disc washer method. So again, you have to know, is this going to make a disc or is it going to make a washer? And you know that if something's beveled out in the center or if there's a hole in the middle, it's going to make a washer. If it's a solid figure through and through, then this is going to be a disc. Okay? So make sure you know which one of those to use as far as your formulas page. Otherwise, your formulas page won't do you any good. Another thing that I want you to notice is a lot of people get confused. Am I doing top, bottom, right, left? Which variables do I need? So on and so forth. If you will use that formulas page, it tells you what your boundaries need to be and what your variables need to be. If you know what your boundaries and variables need to be, then you know if it's the top, bottom, or right, left. Okay? So for in other words, for the disc method, if you are revolving about the x-axis, you need x boundaries and x variables. And if you can't remember that, it's on your formulas page. Just look. Okay? So don't let that throw you off. All right. So this is the one that we left off with last week. This is a washer method, and I know that it's washer method because if I cut a splice, if I took a splice out of anywhere on here, then it would make a hole. So that's why this is going to be the washer method. That's how you can tell the difference between the washer and the disc method. So we talked about how when you use the formula for finding the volume, and again, you can go to the formulas page. Now the reason why this one has 2 pi is because we did use symmetry on it, okay? If you're not using symmetry, then it's just pi, and then it'll go off your formulas page, and you have your pi times your function squared. Okay, so let's look at this one. It says find the volume of the region bounded by the graph of x equals the square root of y and x equals 2y revolved about the y-axis. Now, out of that problem, before you go any farther, this is what I want you to do. I want you to see that we are revolving about the y-axis. So I want you to go to your formulas page, and I want you to notice that either we're going to use the disc method or we're going to use the washer method, but since I'm covering the washer method, you should know that it's the washer method. But let's draw this. If we're going about the y-axis, in other words, this is well, if it's a y-axis, you're going to use y boundaries and you're going to have y variables. Either way, it doesn't matter if you're using this method or the washer method. Either way, you have y boundaries and y variables. Okay, so let's graph this. If we have x is equal to the square root of y, x is equal to the square root of y is backwards to what you're used to seeing. You guys are used to seeing y is equal to the square root of x. And we know that that's looks like that, right? Well, what happens if we change the symmetry? If you have x equals the square root of y, what is that going to look like? And if you don't know, what can you do? Use a t-chart. Well, if I make y 0, what is x going to be? 0. If I make y 1, x is going to be 1. If I make y 4, what's x going to be? Okay, so we're going to go like that. And we're not going to do plus or minus. Why? I heard plus or minus. Why are we not doing plus or minus? Because we did not initiate the radical. The radical is already there. Okay? So, that's what x equals the square root of y looks like. Now, we have x equals 2y. And again, that's backwards of what you're used to, but you should at least know that this is a straight line, right? It is a straight line, and if you wanted to solve it for y and put it in slope-intercept form, you just divide both sides by 2, and you have y is equal to 1/2 x plus 0, right? So you can graph that. You have an you have a y-intercept of 0, and then you rise 1 and run 2. And so it's this line here. So, we are looking at, again, a tiny, tiny area like this right here. Okay, so do you see that little bitty red? That's what we're looking for. Okay, and it's asking us to take this about the y-axis. So if we take this about the y-axis and we make this a solid figure, it's going to make kind of like a bowl. Do you see that? Because you're going to have the outside, and then you're going to have that straight line. So it's going to kind of like make a bowl. So you can see that this is going to have to be the washer method. I guess I should have taken that all the way down. Because you do have a beveled out center. So it is going to be to the best of my ability. Do what now?
Does that one line touch the other line?
They intersect. Mm-hmm. Yeah. Watch this. Your square root is going to do that. And then your straight line is going to do that. Did you see it that time? Okay. So there is a little bit of area in there. Okay. So again, when we take that around, it is going to be a bowl. And since it's going to be a bowl, the inside is going to be beveled out. So that is going to give you a washer. Now, since we're going about the the y-axis, it's going to be the formula at the very, very bottom of your page. And the formula says that the volume is equal to, just coming straight off the page from C to D, pi times the function of y squared minus f of g, g of y squared dy. Okay, and so you remember your radius, right? When you do the washer method, it's going to be your larger radius minus your inner radius, your smaller radius. Big radius minus small radius. Okay, so volume is going to be equal to. Now we can pull pi out front because it's a constant. We can always pull our constants out front. Okay, from C to D, we know that they both start at 0, right? So we know that that's going to be our lower boundary. And it looks like, due to my human error, it looks like the upper boundary is 1. But let's make sure, okay? How do we make sure? Remember, if you have x is equal to the square root of y and x is equal to 2y, we can set x equal to x, right? So we'll have the square root of y is equal to 2y. How do you get rid of a square root? Yeah, you square both sides. So if I square both sides, I'm going to have y is equal to 4y squared. Now that I have a quadratic, I can get this set equal to 0. And then turn around and factor. And so yes, y is equal to 0, but then you have 4y minus 1 is equal to 0. So for this case, what is y? 1/4. So that upper boundary is not 1, it's 1/4. And again, it's due to human error. I mean, I drew that to the best of my ability. So they actually intersect at 1/4 at the top. Okay, now, we moved pi out, so we don't have to worry about that anymore. But let's look at let's figure out which one's going to be our bigger radius. Which graph is the farthest from y? Your line or your parabola? Your parabola, your half parabola, I guess you could say. So let's turn that into y to the 1/2, okay? Squared. Minus, and then of course your line would be the one that has the shorter distance from y. So your line is going to be 2y squared dy. All right, let's do some math. So volume is going to be equal to, again, leave your constant out there, from 0 to 1/4. And anytime you square a radical, that's going to go away, so you're going to have y minus 2y squared is going to be 4y squared dy. All right, so that's all the algebra. Now we're ready for the calculus. Calculus part says to integrate. So I'm going to have the volume is equal to pi times the antiderivative of y is going to be y squared over 2. The antiderivative of 4y squared is going to be 4y to the 3rd over 3. And we're going to integrate from 0 to 1/4. So that's the calculus part. Now all we have to do is the math part, which again is just pure calculator. So you tell me, what is y squared 1/4 squared divided by 2? 1 over 32. 1 over 32. Minus 4y cubed over 3 if you plug 1/4 in. So you're going to do 1/4 cubed times 4 divided by 3. What are you going to get? Minus 1 over 48. Okay, so you have your upper boundary minus your lower boundary, right? So you're going to have 1/4 minus 0. Well, when I plug 0 into both of those, what happens? It goes to 0. So we don't even have to worry about that. All right, so what is v equal to? In your calculator, do 132 minus 148, or 1 over 48. And you should get 1 pi over what? 96. Good job. Questions? Are we good? Okay. Let's see if we can find our way through this one. This one, I will tell you that the algebra on this is absolutely horrific. It's doable. I was working this problem at my desk, and I actually went all the way through, and it took me approximately 30 minutes to get through all the algebra. So, That's why it says we're going to do the setup only. Okay, I'm interested in, can you do the calculus portion of this? Okay, the algebra portion of it, obviously if it takes me 30 minutes to do it, it's going to take you a little bit longer, and I would never put something like that on the test. However, I could put something like this on the test and ask you to just set it up. Okay, now, what makes the algebra so bad is the fact that if you'll notice, we're revolving not about an axis this time. We're revolving about the line x is equal to 4. And that's what makes the algebra so nasty. And what I want you to do is that if you have your book, I want you to look in your book. The problem starts on page 319. Notice, well actually you can do the one from example 3 also. Look at example number 4. It says find the volume of the solid generated by revolving the region described in example 3 about the line y equals 3. So what they did is they took the problem from example 3, and you can see the shape drawn in figure 6.26, in particular number 2. And then look what it says. It says to take that problem, but this time they want you to revolve it about the line y equals 3. So you're taking the whole graph and you're moving it up 3. Do you see that? So now what you're doing is you're revolving this shape around x or y equals 3. And what that does is it changes a couple of things. And it makes it a little bit crazy. So let's go ahead and graph the one that's on the board.
I just have a question.
Okay.
Why would they want to move it off of the easy spot when it's the same area and volume?
Well, if you take your two-dimensional, it's not. It actually increases. If you take that region, look at figure 6.27. If you take that region and you revolve that region about a different line, y equals 3, what's going to happen is the volume, depending on which way you're moving it, either one, your volume is going to stretch, or it's going to decrease, depending on which way you're moving. Okay.
So it's not just
Do what? Okay. So you have y is equal to x to the third power. Y'all know that that's the Superman curve, right? And then you have y is equal to 4x. So it starts at 0 and then it rises 4 and runs 1. So that line is here. And so what we have is these two regions here. But what we're going to do is we're going to revolve this solid figure, this two-dimensional figure, into a three-dimensional figure by rotating it about the line x is equal to 4. So this is going to be our new axis of rotation. Okay, now, two things happen. Number one, if we had rotated this thing, and Frank, maybe this will help you out. If we had rotated this thing about just the y-axis, it would have been symmetrical, right? No big deal. But what we're going to do is we're going to take this thing and we're going to rotate it about the x equals 4 axis. So now what's going to happen is the bottom part of our figure is going to be bigger and the top part of the figure is going to be smaller. Can you see that? So the volumes are going to be different. The volumes are going to be very different. The lower part's going to have a larger volume than the top part because it's closer to our axis of rotation. Can you picture that in your head? Because I could not draw this if I tried. So hopefully you can get a picture of that. Okay, so what does that do? Well, since we're revolving about x equals 4, x equals 4 is a vertical line. Which of our axes is comparable to x equals 4? X or y? The y-axis. So on your formulas page, you're still going to do that r sub y region. You're still going to use that formula. Okay? So when you do this, what's going to happen is you're still going to have your integral. For the first one, we're going to go from 0 to 8. You cannot use symmetry. Yes, I know that our discussion earlier, technically our graph goes from -8 to 8. If we were revolving it about the x-axis, you could use, the y-axis, you could use symmetry. But since we're not, you cannot use symmetry. Okay? So symmetry's out the window on this one. Okay, so we're going to go from 0 to 8 to get the top half first. And then what we're going to do is we're going to go from -8 to 0 to get the bottom half. And then we're going to add those together. If we were going to go all the way through the algebra, but we're not. Okay, so the top half says that we're going to go from 0 to 8. Now, according to your formula, of course you have pi and you can move it out front. But then what you have is you have your bigger radius from your axis of rotation. Which one is that going to be? Is that going to be your line or is that going to be your S-curve? From your axis of rotation. Is it the line or is it the S-curve? Looking at the top graph, which one is farthest? Which one is the farthest away from this line? The line. The line is. Okay. But now there's another problem. Do you see what the problem is? We're using y boundaries. So we need y variables. Okay. Right now you're telling me the line. Can I use 4x? No. If you're in a r sub y region and you're using y boundaries, you cannot use x variables. You have to use y variables. So what I need to do is I need to go somewhere on some scratch paper or something, and I need to take y equals 4x, and I need to solve it for x. So basically you get x is equal to 1/4 y. That I can use. But before you put that into your formula, since we moved 4 units off of your y-axis, I need to somehow put that into our formula because, like I said, that is going to change your volume. So what you're going to do is you're going to put here 4 minus your line, which is 1/4 y or y over 4, however you want to put it. Do you understand where that first 4 came from? It's 4 minus because that's your new radius off of your y-axis. Okay? Okay, go back to your formula. Minus your inner radius, which again is still going to have the 4 minus in there. And which one's the closest to x equals 4? That's going to be your S-curve. But look, we have another problem. We can't use y equals x to the third because we need y variables. So instead, what we're going to have to do is take the cube root of both sides. So we're going to use y to the 1/3. And square that. And of course it's dy. So that's the top half. Again, the algebra is crazy. If you want to try it, you can. You're going to have to do square, double square on both of these. But that's only the top half. Now what we're going to have to do is we're going to have to add the bottom half. So the bottom half, we're going to go from -8 to 0. Now let's look. We're still going to be 4 units off the y-axis, so we do have to put that into play. But now look, which graph is farther away from your x equals 4? Your S-curve. So this time you're going to have 4 minus y to the 1/3 minus 4 minus 1/4 y squared. And once you add those together, you will actually get your volume. Megan, what's wrong?
I'm just kind of confused about how it's 4 minus.
It's right minus left.
Or would it be 4 minus like?
It's opposite of what you think.
I'm just like, because I'm trying to account for that's similar to the part up there, but it's smaller.
But your graph is on the left-hand side.
Right.
So it's going to be 4. It's going to be 4 minus irregardless
Okay.
because your graph's on the left-hand side.
Okay.
If your graph were on the right-hand side, then you would have your graph minus your boundary, or your graph minus your new radius.
I think the problem is I'm thinking of like the line is like a cylinder plus that little added on part. I don't think that's
The line that we
Like, I'm
graphed, the
thinking
y
like-
equals 4x line.
right, because the bottom, if you just did from 0 to 4 for x, it would make a cylinder, and then I was thinking plus the graph on the
Plus the S-curve.
right, but like
It's not really going to make a cylinder. It's going to make more of a cone shape with a beveled outside, or inside rather. On that one, the inside's going to be beveled, curved, and on the outside, it's going to be curved outward.
So it's rotating around.
X equals 4.
If it was rotating around x equals -4, you would.
It would, if we're going to do one like that. If your graph was on the right-hand side,
You would do what you just said. Add. So no, subtract the
you
graph.
would flip-flop them.
Yes.
You would flip-flop them.
That's all I got.
Anything else?
I have a question about your, I guess it's called the boundaries, your 8 and 0.
Uh-huh.
Okay, hard to do the 8. And I can see it on the graph a little bit, but
Right. Well, it's just because I know that if I plug, for example here, I know that if I plug 2 in for x, it's cubed, I know that y is going to be 8. And, okay, let's go back to the algebra, I guess. I can say 4x is equal to x cubed. And so x cubed minus 4x is equal to 0. And so if you do the algebra and factor out an x, you're going to get x is equal to 0, which is the center. That's the turning point. And then you're going to get, and again, this will factor. So you get x is equal to plus or minus 2. So if you plug that in, if you plug the plus or minus 2 in for that y cubed, you get that upper boundary and that lower boundary.
so you have to take that and plug it into the x.
Because you need y boundaries. Because you need y boundaries. Otherwise, you would have to take, which would be craziness, but you would have to take 1/4 y is equal to y to the 1/3 and go that way.
Okay.
And you can, but to me, it would be easier to find the x boundaries and plug it in to find y.
Okay.
You see what I'm saying?
Yeah, I did all that except that last step right there.
It depends on, do you need x or do you need y? And in this one, it's easier to solve for the x coordinates, I guess you could say, and then plug them into your function and come up with the y boundaries. But if you wanted to go straight for the y's, you could
So
take
that
the
was
cube
easy.
root of both sides. Yeah, whichever one's easier. So, well, now I'll go with it. Anything else? Okay. Let's try one more. And again, we're just going to do the setup. All right, so let's get this thing graphed. It says find the volume of the region bounded by the graph of y equals 1 minus x squared. You're probably used to seeing it written like this, and this is fine. So if you have negative x squared plus 1 from your pre-cal days, you should know that this is an upside down parabola shifted up 1. And if you don't know that, use your T-chart. You can do that. Just plug in some numbers. Okay. Then you have a straight line. You have x minus y is equal to 1. It's in standard form, so I'm going to graph it in standard form. So I know that x is equal to 1, and I know that y is equal to negative 1. So you have this line here. So the region that we're talking about is in here. But we're not revolving about an axis. Instead we're revolving around y is equal to 3. So y is equal to 3 is a horizontal line going through the y-axis at 3. All right, so we have shifted it. So my question to you is this. When you look at this and we shift our axis of rotation up to y is equal to 3, which axis does y equals 3 look like? Your x-axis. So that tells you which formula you're going to use on your formulas page. You're looking at an r sub x region. You're looking at an r sub x region. Okay, so volume is going to be equal to, let's look at our boundaries. If we're looking, look at your formulas page, okay? Don't look at what I'm doing. Look at your formulas page and figure it out for your own, for yourself. If I'm looking at an r sub x region, where do my boundaries need to come from? That's not going to change. Even if you're not going about either of the axes, you're still going to have to get your boundaries the same way we've always gotten them. So what axis are your boundaries going to come off of? Your x-axis. If you're in an x region, you need x boundaries. Okay, so if I need x boundaries, you can kind of sort of tell maybe where these two intersect. But not exactly, maybe. So go to your algebra, okay? I already have an equation that says y equals. So what I'm going to do is I'm going to take this line and I'm going to make it into y equals. So that's going to be y equals x minus 1. And now what I can do is I can set those equal to each other. Okay? And now I can find my x boundaries for sure. All right, it's a quadratic, so we need everything on the same side set equal to 0. I don't want a negative x squared, so I'm going to move everything to the left. So I'm going to have an x squared plus an x minus 2 equals 0. Factor. So we'll have x plus 2 and x minus 1. So x is going to be negative 2 and x is going to be 1. So there's your boundaries from negative 2 to 1. Okay, now, pi, of course, your pi can go on the outside. Don't have anything for that. All right, so now you need your outer radius minus your inner radius from your y equals 3. So which one's going to be the farthest from your y equals 3? The line or the parabola? The line. So that's the one that's going to come first. But what am I going to do? It's top minus bottom. Your graph is on the bottom side. So, and you have to take into account that we shifted our axis of rotation up 3. So you're going to put 3 minus. You need x variables because we have x boundaries. So that's going to be x minus 1 and all that squared plus 3 minus. And again, if you want to clean that up a little bit, you can, but it's totally not necessary. Since I say set up only, I want to know, do you understand the shift, basically, is what I'm asking. This one will be minus. It's going to be top minus bottom, so it's your line minus your graph. On the other one, it was right minus left, so it's your line minus your graph. Okay, so again, if I ask you to do one of these on the test, it is going to be just set up only, okay? If we shift it off of the x-axis or the y-axis, it will just be set up only because I don't want you to spend too much time doing some algebra. And two, it may just be a bonus problem. I don't know. We'll see. All right, any questions about dishwasher method?
We ever have to like set a big problems where the line that we're revolving around is not more than on the vertical line?
Nope.
Okay.
Nope. Not right now, anyway.
I don't quite understand everything on this right here.
What do you not understand? Tell me.
The second part of that, that's the equation.
This here?
Yes.
Okay, 3 is our shift.
Okay.
So it's top minus bottom, but we're on the inner radius. The graph closest to this line is that parabola. And so I need x variables. And there it is. So it's 3 minus your inner graph, your inner radius.
Okay, but that plus sign right there in the middle.
That's what I'm confused.
To the left of it.
Oh, in the point, it's minus. Is that what you were saying a while ago, Amanda?
Yeah.
You're right. You're right. Thank you. It would help if I wrote the formula down. It is minus. Formula. What else?
But we don't have to do a second part because there's not two things.
That is the second. This is the
You
second
know,
one
it's
here.
like on the last
Like
one.
on the last one.
Oh, right.
Because it was bigger. Or because it had 2 centimeters.
Right. And that would be easy to pick out, right? Because if you saw symmetry, But when you're, just be careful when you're doing volume. I would not do symmetry on any volume problems like that anyway, if you're shifting them. Because when you shift it and you rotate it, it throws your volume off. It skews the volume tremendously. So I wouldn't do any symmetry on shifting of volumes. Okay, let's talk about one last thing, and that is it's finding volume. So it's still the same concept. We're still finding volume. However, instead of using a disk method and instead of using a washer method, we're going to use what we call a shell method. And if you look on page 322, 323, you will see what I'm talking about. Also, on your formulas page, it's number 3, and I have it labeled for you. It's called the shell method. So you may, for me, I just turned the page over. For you, it may be a different page. I don't know. Okay. So now, talking about the disk washer method. When we talk about a graph, a solid graph, and we cut a disk out, you know that that disk is solid through and through. Also, if we have a solid figure and we cut a section out and there's a hole in it, that's your washer. Well, now what we're going to do is instead of doing a section, we're going to do a cylinder. So if you'll look on page 323, and you can go through there if you want to, but what I want you to look at is I want you to compare picture number 2 to picture number 4. Picture number 2 is the solid that we're trying to find the volume of, and picture number 4 has cylinders, and hopefully you can see the building of those cylinders. You have that inner cylinder, and then you have another cylinder on the outside, and then another cylinder, and another cylinder, until you get all the way to what looks like our old washer. But they're all cylinders, okay? And so this is called the shell method. And what we're going to do is we're going to find the volume by using cylindrical shells. And so that's going to change our formula just a little bit. Because you know, in order to find the volume of a cylinder, it's different than finding the area of a circle, right? All right, so look at your formulas page, and there's a couple of things that I want you to notice. Look at number 3, called the shell method. And what I want you to do is I want you to read to yourself the first description and the formula, just the first one. And I want you to tell me what you notice. It's backwards from what we're used to. That's the one significant difference. Okay? So on the test, I will tell you, use either the disk washer method or I'll say use the shell method. Okay? So that'll make it easy for you. You're only going to have 2 options. You're either going to use the disk washer or you're going to use the shell. And I'll tell you on the test which one I want you to use. Now, why is it backwards? Go back to your book. Look on page 323 and look at those shells that we're talking about. And it all has to do with now the radius. Where is the radius? Your formula says integrate, of course, from a to b, 2 pi x. X is called the average radius. So what they're doing is they're taking each one of those shells and averaging the radius together. But as long as we're revolving around either the x or the y axis, your radius is going to be either x or y. Look at this. In picture number 4, we're revolving around the y axis. So if you're revolving around the y axis, the average radius of any one of those cylindrical shells is w sub k, which we're going to call x. Because if you move out from the y-axis to the right, you're moving out an x distance. Do you agree with that? If you're moving from the y-axis out towards those shells, you're moving a distance of x depending on which shell you're at. So the average radius at any point would be x. So in your formula, that's why you see 2 pi x. Okay? 2 pi comes from your volume of a cylinder. X is your average radius. And then what we're going to do is we're going to multiply that times your actual function. Okay? So, the main difference, the main thing that I want you to understand is that everything's reversed. But don't let that throw you because you have your formulas page. If your problem says revolve this about the y-axis, go to your formulas page and follow the formula. Write that formula down and plug in everything you need in order to work the problem. Okay? At this point, you guys should know if we're going from A to B, you're looking at x boundaries. If we're going from C to D, you're looking at y boundaries. You should know that by now. Okay? So, here are your formulas. The main thing I want you to understand is this average radius. Average radius is this x if you're going about the y-axis, and the y if you're going about the y if you're going about the x-axis. Reason being is because, like I just said, if you're going around the y-axis, your average radius is going to be x. If you're going around the x-axis, your average radius is going to be a y distance. Okay? That's why that is. Now, you can imagine that when we shift these, and we will shift them, when we shift these, your average radius is going to be off by that shift, just like what we just came through. Okay? But if you're not shifting off of the axes, then you're either going to have an average radius of x or an average radius of y, depending on which way you're rotating. And then, of course, your functions, there's no difference for your functions. Okay? So, let's look at this one. Find the volume of the solid generated by revolving the region bounded by the graphs of y equals 1 over x, x equals 1, x equals 2, and y equals 0 about the y-axis. And so let's graph this first of all. You know that 1 over x, hopefully you know, that 1 over x looks like this. And you also know that it's in the first quadrant and the second quadrant. I'm sorry, the third quadrant. But the third quadrant's not going to come into play, so it's irrelevant. The next one you have is x equals 1. So x equals 1 is this line here. And then you have x equals 2, which is that line there. And then you have y equals 0, which is your x-axis. So what region are we talking about? We're talking about this region right here. Now, what are we doing with this? We are rotating it, revolving it around the y-axis. So what I want you to do is I want you to go to your formulas page. If we're rotating this about the y-axis, write down the formula if you need to. Volume is equal to the integral from a to b. And you have 2 pi, which of course we're going to move out front. X is your average radius. X is your average. Why is x my average radius? Why is x? What is your average radius? Your average radius is the distance away from your axis, the whole graph from your axis. Well, if we're going about the y-axis, right now it looks like the graph is a unit away. But remember, we're rotating it. And it's going to go about. So for every shift you have to the right, you're going to have that exact same shift to the left, right? So they cancel out, so your average radius is still going to be x. So you're going to have 2 pi x times, still working off the formula, f of x dx. Okay. So my boundaries are obvious, right? You have x boundaries, What are they going to be? From 1 to 2. So that should be kind of obvious. 2 pi is a constant. We're going to move it out front in just a second. Times my function. When you do these, listen to me, okay? When you revolve around the y-axis, it's opposite of what you think. When you have x-axis boundaries and x variables on this one, top minus bottom. Okay? So what's your top function? What's your top graph? 1 over x. What's your bottom graph? 0. So 0 is not going to come into play here, okay? But just keep that in mind that you do have a top minus bottom or a right minus left, depending on what you are. Okay, so this is top minus bottom, so it is going to be 1 over x dx. And do you see what I did? I just plugged in the formula wherever I needed to, okay? If you need to, just so you know that it's there, it is top minus bottom. Okay, the 0 is not going to come into play. It's going to go away anyway. So, but it is there. Okay, let's start doing some work on this. Let's move the 2 pi out if you haven't done so already. Can't move the x out because we are integrating with respect to x. Times 1 over x, and the 0, like I said, doesn't come into play. What happens when you multiply x times 1 over x? What do you get? You get 1. Can you tell me the antiderivative of 1? Good. Does everybody understand why the antiderivative of 1 is x? We talked about it, I think, earlier. If you have 1 x to the 0 power, that is 1, right? Up it by 1 and divide by 1. Okay, so let's plug in. So we're going to have 2 pi. X is going to be 2. Then x is going to be 1, top minus bottom. So you're going to have 2 pi times 1, which of course is 2 pi. See what? You don't like that? Why?
Because we did all that to start.
Just to get 2 pi?
What we started.
Well. Okay, the shell method will probably, I know it doesn't seem like right now, but the shell method will probably become your method of choice to find volume when you have choice. Okay, on the test, I'm not going to give you a choice. But when you do have the choice, for example, on the final exam, you'll probably want to use the shell method. I don't know, you may like the other one better. The thing about the shell method is you don't have to decide, okay, is this disc or is this washer? It's shell, period. Okay. All right, so let's try this one. Find the volume of the solid generated by revolving this stuff about the y-axis. Okay, so we're going off of the y-axis, so you have your formula, yes? Let's graph this. So I have y equals x to the third plus 1. That's your Superman curve, shifted up 1. So it's going to come in like this. And then you have x plus 2y is equal to 2. That's in standard form, and I'm going to go ahead and graph it. My x-intercept is going to be 2, and my y-intercept is going to be 1, so it's this line here. And then you have another one at x equals 1. So it's going to be here. So you're looking at that little triangle sort of shape. All right, so we're going about the y-axis. So you have your formula. Now, we need x-axis boundaries. Do you know what the x-axis boundaries are going to be? for sure, what can you do? You can set them equal to each other, right? You can either take, well, I guess the easiest thing to do would be to take your line and solve it for y, and then set y equal to y and solve. But you should get 1. No, you should get 0. X boundaries. You should get 0. And then, of course, your other boundary is going to be what? All right, so your X boundaries are going to be 0 to 1. And, of course, we have the 2 pi. We're going to go ahead and put that out front, though. That would be some crazy algebra. Look. Okay, so do you see what happened on that? I know it's some crazy algebra, so it's nice to know that the X boundary is 0. But if you take those two and you set them equal to each other, and then of course you get it set equal to 0. Well, when you get it set equal to 0 and you factor out an X, you're going to have X squared plus 1/2. Well, when you take the 1/2 over, you get the square root of -1/2. That is not a real number. And remember, in calculus, as of right now, we only deal with real numbers. So this is not an option. So it has to be 0. So that where the S curve and that line intersect, that is going to be 0. And then, of course, the other boundary is obvious. It tells you right here. Okay? So we're going to go from 0 to 1. Now, you have your average radius. What's the average radius going to be? X. And then, are we going to do right minus left or top minus bottom? All right, so what we're going to have is just be patient with this, okay? It's work, but be patient. Okay? So, which one is your upper curve? The S curve. So we're going to have x times x to the third plus 1 minus the bottom. What's the bottom curve? That's going to be your line, but I only need x variables. And we already did that, didn't we? -1/2 x plus 1. And of course it's going to be dx. Okay, so let's clean this up a little bit. So we're going to have 2 pi times the integral from 0 to 1. Let's leave the x out for just a second. Let's go inside here. You have 1 minus 1, so those 1's are going to cancel out. That's nice. And so then you're going to have x to the third plus 1/2 x. Does that look a little bit better? And we still have one more step to do. What can we do? What can we do? Yeah, distribute. Yeah, that looks a lot better, right? Can you integrate this? Hopefully. I think you can. So we have 2 pi times the integral from 0 to 1. Oh, nope, we're going to integrate. Never mind. Sorry. X to the 5th over 5 plus 1/2 x to the 3rd over 3. And you know what that's going to turn into, x to the 3rd over 6. Integrated from 0 to 1. Okay, so if we plug the 1 in, what are we going to get? One-fifth plus 1/6. And the 0 is not going to come into play, right? All right, so what are we going to get? Somebody tell me. What? Me 11 pi over 15, or 22 pi over 30, which will reduce. Either way. Okay, so when we say everything is reversed, you just have to know that if we're doing x boundaries and x variables, then it's top minus bottom. Whereas if you're doing y boundaries and y variables, it's going to be right minus left. So that didn't change. Okay, let's do one more before we go on break. Let's do this one. You try it all by yourself. Okay. For the first one, you have y cubed is equal to x. If you had y equals x cubed, that would be your normal Superman curve. Okay? But since it's kind of backwards, all that happened is we're taking that and we're flipping the symmetry. But if you don't know what that looks like, guys, look. All you've got to do is pick some numbers for y. So, for example, if y is 0, x is going to be what? 0. If y is 1, x is going to be what? 1. If y is negative 1, x is going to be what? Negative 1. If y is 2, what's x going to be? So if y is 2, x is going to be 8. And if y is negative 2, what's x going to be? Negative 8. So watch this. We're going to have 0, 0. We're going to have 1, 1. We're going to have negative 1, negative 1. We're going to have 8 all the way out here, 2, way off the graph. And then we're going to have negative 8 all the way out here, negative 2. So do you see what I'm saying about the symmetry being off a little? So this is going to be your y to the 3rd, or x equals y to the 3rd curve. And if you don't know what it looks like, graph it, please, because especially if you depend on those graphs, if you're going to depend on the graphs, you need to make sure you know how to graph it. Because if you don't know how to graph it, it's going to throw your problem off. Okay. Now, let's talk about this one. Y equals 3. Now, this is how I teach my algebra, my Math 100 students. That's what I was going to say my algebra 1 students. This is how I teach my Math 100 students. With this equation, y equals 3, which variable do you see? You see the y variable. Therefore, this line has to go through the y-axis. It will never touch the x-axis. It has to go through the y-axis. Where do you think it's going to go through the y-axis? At 3. So that's this line. And then, of course, x equals 0 is this line. Now, again, like I said a while ago, if you kept drawing these are actually going to intersect, but they don't intersect until 27.3. And that's okay, because we just need to know the y boundaries. Since we're revolving around the x-axis, we just need to know the y boundaries. So the y boundaries are going to be from 0 to 3. Okay, I'm going to go ahead and move the 2 pi out front. Now, what is my average radius? Is it going to be x or is it going to be y? It's going to be y. Now, when we talk about what function are we going to use? Well, when you do this, since we're using the y boundaries, you're going to do right minus left. So what is the right side function? It's your Superman curve, is it not? So you're going to have times y to the third minus your left side function, which is going to be what? 0. So really it's not going to come into play. So we're going to have 2 pi integrated from 0 to 3 of y to the 4th power dy. And I said, that's like I said, once you get it set up, the actual calculus and the math is not that bad. Okay, so let's integrate. Um, 3 to the 5th over 5, whatever that is. 3 to the 5th over 5. And then times 2, 486 pi over 5. So again, this is the area that we're talking about. And it does keep going all the way out here to the point 27.3. And we're going to take that and we're going to revolve it about the x-axis. Try another one. You have questions about this one? Try this one. Make sure your graphs are correct. Graph and then go on break, and then we'll ponder over break how the setup's going to be. All right, so you have 2y is equal to x. Well, that's fine for when we put it into the integral, because since we're going about the x-axis, we know that we need y variables. So the equation that they give us is great because it is set up with a y variable. But graphing that, we're not used to that, right? So we can put this in slope-intercept form in order to graph it. So we know that we're going to go through the origin. And we're going to rise 1 and run 2. And you can go backwards if you want to. Whatever. So there's your line. And then you have y equals 4, which is going to be here. And then you have x equals 1. And so the region that we're going to set up our integral for, the region that we're going to find the volume for, is right here. Now, Out to the right, I don't know where they intersect. Does that matter? To the right, it doesn't matter because we need y boundaries. So we're going to get our boundaries off of basically where they intersect closest to the y-axis or where they intersect on the y-axis. We're not on the y-axis, we're off the y-axis, which is going to come into play. But look, we're here and we're here. So can you definitely tell me that we're intersecting at, I don't know, 0 or 1 and then all the way up to 4? The upper boundary is obviously 4, right? The upper boundary, there's no question about. The upper boundary is going to be 4. The lower boundary, though, is the one that I have a question about. If you tell me that it's 0 or 1, you're totally guessing, which is fine, but you're wrong. So let's go on break, and then we'll find that back. All right, so our lower boundary we found to be 1/2. And again, all we did, since we need the lower boundary, we figure out where the two graphs on the bottom intersect. And we use them either through substitution or filling with each other, give us one and the same. And figure out what y is going to be since we need a y boundary. And the easiest way to do that is take x equals 1. Take that 1, plug it into your line for x, and you come up with 1/2. So that lower boundary is 1/2. So be careful with that. Don't automate unless it is extremely obvious. Now what do I mean by that? Remember the problems where we were looking for x boundaries and you actually had lines that said x equals 1 and x equals 2? That's when the boundaries are obvious, okay? Other than that, be very careful. If you're not 100%, make sure you do some algebra to figure out those boundaries. Okay, so let me make some room here. All right, so again, we're on the x-axis, so we are going to use our x formula. So we have our 2 pi, we moved it out front. Our average radius is going to be y. Now, in order to do this, we're going to do right minus left. So what is the right side graph that does not act as a boundary? That's how you have to look at it. What is the right side graph that does not act like a boundary? What's it going to be? It's going to be your line, right? So it's going to be 2y minus. So this is where it's a little bit different than before. What is the left side? It's right minus left. So what is the left side graph? 1. And that will come into play this time, right? That will come into play this time. And so we're going to have dy. Okay, so do a little bit of work here. Again, just be patient with it. So we'll distribute. Now we can integrate. So if we integrate, we're going to have 2y to the third over 3 minus y. Why did I do that? Again.
And then you're thinking a little bit, but I'm confused as to why the left is 1, because it is in terms of y, y's are defined. Isn't it? Or, because it would be when you have like x plus, or x equals 1 with 0 y, so the solve for y would be x minus 1 over 0.
You don't have a 0y. You actually don't have a y-intercept at all. But x equals 1 is the 1. X equals 1 is your function on the left-hand side. So you could say, so that's your f of y function, or g of y, whichever. We're not looking at it in terms of variables per se. We're looking at it in terms of what is the name of the function to the left side. So it's the name, the identifier of the right side function minus the identifier of the left side function, the name of the left side function. So the name of the right side function is 2y. And the name of the left side function is 1. Is that better? Does that help? Okay. And when we say in terms of y, the only thing in terms of y really is the anti-differentiation with respect to y.
Okay.
Is that better? Okay. So now the fun begins. Okay, so we have 2 pi times. Let's do that upper boundary 4 first. So we'll have 2 times 4 to the 3rd power over 3 minus 4 squared over 2 minus that lower boundary, 2 times 1/2 cubed over 3 minus 1/2 squared over 2. From there, it's just pure calculator work. Did anybody come up with an answer yet? $833 pi? 833 pi over 12. Good, Amanda. Not so bad, right? Okay. So let's get off of the axes and let's actually try to shift these things. And maybe after we do these next 2 problems, it'll help get the shift straight in your head, hopefully. So let's look at this one. And again, we're going to do the setup only because the algebra is atrocious when we shift it. It's not, it's not hard. It just takes forever. And we don't have forever, unfortunately. If this was a 6-hour class, we would have plenty of time. But it's not, and it's summer semester at that. So we don't have enough time to do all that wonderful algebra that I would love to do. Okay, so if we have the first equation, y equals 4 minus x squared. Again, you're used to seeing that as y is equal to negative x squared plus 4. So you know that that is an upside down parabola shifted up 4. And then you have y equals 0, so that's going to go through the y-axis at 0. So that's this one. Now, we're talking about this region. But look at A part. Instead of our axis of rotation being the y-axis, and I kind of gave you a hint there, we are going to have a axis of rotation at x is equal to 2. So there's our axis of rotation. Okay. So if we say that we're going to rotate about x is equal to 2, which axis is that comparable to? The y-axis. It's comparable to the y-axis, so that tells you which formula you're going to use. It's comparable to the y-axis, so we're going to use the top formula. So we are going to have our boundaries. Our boundaries are going to be x boundaries. Now, for this one, we can go from -2 to 2. Again, I would not use symmetry on these things that are being shifted. I just wouldn't. If you're shifting, don't use symmetry. Okay, so if we go from -2 to 2, And of course, the 2 pi. You can move it out front now or you can move it out front later. It doesn't matter. Okay, average radius. That's what's going to be different. Okay? For your average radius, and again, I'll tell you what. Look. Okay. Look in your book on page 324. And you'll see a pink box. And in that pink box is kind of guidelines on how to set these things up. It's nothing more than what I've already told you. You can read it if you want to. But look down at number 3 and look at the italicized words. This will help you understand what average radius is, more so than what I've already told you. But just read it. It says, remember that x represents a distance from the y-axis to a vertical rectangle, which is what one of our shells. And y represents a distance from the x-axis to a horizontal rectangle. So I told you that earlier when I was describing average radius to you. Well, now go over to example number 2. And you see where it says solution? Go down to the last sentence. And read this. Remember, it says, it is important to note that since x is the distance from the y-axis to the rectangle, the radius of the shell is going to be 3 minus x. Why is that average radius 3 minus x? Look at your problem. It says we're going to revolve this about the x equals 3 line. Okay? So, the shift in your shell problems is going to come into play on your average radius. So, if you're shifting away from your axes, your average radius is no longer going to be x, nor is it going to be y. Okay? You have to take your shift into consideration when you do your average radius. So for this problem, for example, our x equals 2 line is comparable to the y-axis. So instead of using just x, what are you going to use? 2 minus x. Right minus left. 2 minus x. For your radius, it's right minus left because our radius is in the x direction. So it's right minus left. Okay? So you're going to have 2 minus your radius. And then you're always, well, if you have a vertical, for your radius, it's right minus left. For your functions, it's top minus bottom. But get it in your brain. Look at me. Don't get overwhelmed. For your radius, if you're revolving around the y-axis or something comparable to a y-axis, okay, look, your radius goes this way, which is the x direction. And when you move in the x direction, it's right minus left. Okay? So since our axis of rotation is 2, like on the right-hand side, it's going to be 2 minus your radius. So it's 2 minus x. Is that better? Okay. So we're going to have 2 minus x, and then, of course, our function, which we only have one function, so that's nice. So we'll have 4 minus x squared dx. And that's the setup. Okay, now let's look at b. For b, what we're going to do is we're going to rotate this about x equals -3. So we're going to rotate here. Now do you see that your function's on the right-hand side? Your radius is going to be on the right-hand side. Okay, so that's gonna change some things. So you still have your 2 pi. You still have your x boundaries, -2 to 2. But this time, your radius is on the right. It's always right minus left. So what you're going to have is x minus -3 times your function. Which, of course, and you don't have to write this. If you write it initially, that's great. But I think if you write it this way, it helps you understand a little bit better. Okay? So for your radius, if you're revolving about the y-axis or something comparable to the y-axis, your radius goes this way. So it's either going to be x, or if you're shifting, it's going to be, depending on where it is, it's always going to be right minus left. If your line that you're rotating about is on the right, then it's right minus your function. If your line is on the left, it's going to be your function or your radius minus your line of rotation. Okay? Same thing when we revolve around the x-axis, because that's going to be the next problem. Have you got your brain somewhat wrapped around this? Because the next one, we're going to shift left, we're going to shift right, we're going to shift up, and we're going to shift down. Yay. But we're only going to set it up. Okay?
On those A's and B's right there, that first parentheses on the red, you have 2 minus x, and then right below you have x minus parentheses negative 3. I just wondered why you wrote it differently.
Because when you're rotating about the y-axis or something comparable to the y-axis, your radius for your shells are in the x direction. And when you move in the x direction, it's always going to be right minus left. So it's your line of symmetry, or your line of rotation 2, minus your average radius, which is x. But look here, on this one, our line of rotation is on the left. So now it's always right minus left. So it's going to be your radius, which is x, minus your line of rotation, which is a negative 3. Always right minus left. Okay? Is that better?
But this is 2 different things going on here, right? You got 2 different axes, right?
2 different graphs.
Okay.
Yes.
All right.
In A part, you're going to rotate here.
Right.
And in B part, you're going to rotate here. So here, on A part, you're going to take this and rotate that way. On B part, you're going to take this and you're going to rotate that way.
If you actually write down the problem, would you add them together?
No, because they're 2 different
Two
problems.
separate.
They each have their own different
You can't
volumes.
rotate around one thing and rotate.
Well, I mean, they're 2 different problems. I mean, if you want to have a whacked out shape, I guess you could. I don't know.
The one on the left will have a complete hole in the middle, right?
It will. Are we good? Okay. Let's do one where we do shift it every which way but loose. Let's graph it first. The first one, you have y is equal to x squared. You know that that's your basic parabola. And then you have y is equal to 4. It's going to go through the y-axis at 4. So this is what we're doing here. Okay, let's look at A first. A says we're going to, let me make it green. A says that we're going to rotate this about the line y equals 4. Well, look at that. Y equals 4. We've already got it on there, right? So A part, you have 2 pi times the integral. Now, let's stop for just a second. If we're rotating about y equals 4, which axis is that line comparable to? X. So go to your cheat sheet and look. You need y boundaries and you need y variables. Yes? You need y boundaries and y variables. That's not something that you have to memorize, guys, okay? It's on your cheat sheet. You have y boundaries and y variables. So what are your y boundaries? What are your y boundaries? Y-axis from 0 to 4. When you find your boundaries, when you're working on your boundaries, it's just like normal. Don't shift your boundaries at all, okay? It's still going to be from 0 to 4, just like normal. We're going to take that shift into play with our average radius, which would be now, okay? So, now watch this. And I've been talking about this. I've told you this twice, 2 nights in a row that we were going to do this. I don't expect this to catch you off guard. I expect you to know this. All right? If we need y boundaries, what variables do we need? We need y variables. Look at our function. What are we going to have to do? We are going to have to take the square root of both sides. And when we do that, we get x is equal to, anytime you have to initiate the square root, what do you have to take into account? Now watch this. Are you watching? This side of your parabola is your negative square root of y. This side of your parabola is the positive square root of y. Okay? All right. So now, let's continue on with the formula. Now we moved the 2 pi. Yeah, we moved the 2 pi out front, comparable to the x-axis. So we need y variables. Now, so when we talk about the y variables, we're looking at our average radius. For this one, to find your average radius, we're moving in the y. The radius is moving in the y direction, right? Because we're rotating around a different axis. So if you're rotating about a different axis, your radius is going to be in the y direction. Okay? So now, if we're moving in the y direction, your radius is top minus bottom. So it's going to be 4, right? Top, which is going to be 4. So it's going to be 4 minus what? What do you think? 4 minus 1. That is your average radius, 4 minus y. Remember, your average radius is either going to be x or y, or if you're shifting, it's going to be the number with the variable that you would normally use. Where your graph is, your axis of rotation, that's what's going to flip-flop it, okay? But it's top minus bottom, so it's going to be 4 minus y, minus your average rotation.
So could you
Or your average
explain the
radius.
minus y, where did y come from? Does that have anything to do with
It's your
square root?
formula. It's in your, the y comes from your formula. You see the 2 pi y on the shell method, 2 pi y. That y is part of the formula. That's your average radius. Now, let's talk about the function. And this is where the positive and the negative comes into play, because when you talk about your function, it's right minus left. For your radius, it's top minus bottom. For your function, it's right minus left. So what is the right side function? Square root of y. Minus, what is the left side function? Negative square root of y. Very good. dy.
I thought the radius in the last column was right minus 3.
It was because we were rotating it about the y-axis.
Okay. When I see it, I know.
Okay, when you're on the radius part, think about the radius of your shell. So if we're rotating about the x-axis, all of our shells are going this way. So your radius is going this way. But when you go to your function part, it's always, not always, if you're going about the x-axis, it's right minus left.
See it like something.
But if you use your formula page, it should help tremendously. Because if you see that y, then you know you're moving in the y direction for your radius, for your average radius.
Okay, back to that same part again though. That 4 in those first parentheses, that has to do with your axis shifted up to the 4, right?
Mm-hmm.
And then the y, that's your average
Mm-hmm.
radius.
Mhm.
And the negative sign, what is, why?
Because it's top minus bottom. Going back from the very beginning of area, it's top minus bottom.
Okay.
So in this problem, we did top minus bottom first, second one we did top minus
Mm-hmm. And it's because of your
bottom.
radius.
Right.
Mm-hmm. Because in your radius, you're going this way. Okay, let's look at B, see if this helps. Okay, so for B, what we're going to do is we're going to rotate around y equals 5, which is going to be a line going through the y-axis at 5. So we're going to go around this line. So for B, and again, we're only setting the problems up. So for B, of course, you're going to have your 2 pi. And you're rotating around y, so your axis is not going to change. But this time, instead of having 4 minus y, what are you going to have? 5 minus y. And the rest is going to be exactly the same. Now, watch what we're going to do. C part. We are going to take this, and instead of rotating it around something that's similar to the x-axis, we're going to rotate it around something that's similar to the y-axis, because we're going to rotate around this line right here, x equals 2. So let's see if you got this, okay? 2 pi is not going to change at all. X equals 2 is comparable to which axis? X equals 2 is comparable to the y-axis. It's vertical, right? So on your cheat sheet, if we're comparing it to the y-axis, where is our boundaries going to come from? The x-axis. So what do you think it's going to be? Negative 2 to 2. Good. Okay, so now let's talk about the average radius. You know that we're going to have an x in there somewhere, right? Because that's from the formula. That came from the formula. But we have a shift, so we have to take into consideration that shift. So with your radius, we're moving in the x direction, so it's going to be right minus left. Well, is your line of rotation on the right of your graph or the left of your graph? It's on the right, and it's right minus left. So you tell me, where is that 2 going to go? Is it 2 minus x or x minus 2? Very good. Very good. Very good. Now, let's look at this. Watch this, okay? If I rotate this, and you gotta get this in your brain. This is a visual picture in your head. If I rotate this about the upper axis, in other words, if I rotate this about an axis comparable to the x-axis, I have a solid figure, especially for this one. Of course, with this one, you have a hole in the middle, but it's a solid figure. Look what happens. The reason why we had to split this is because part of it was on the right side and part of it was on the left side. That's why we had to split it. Not to mention the fact we initiated a square root. And I told you when you initiate a square root, you have to take a positive and negative into consideration. I've been telling you all that for 2 months now. But, watch this. Now we're going to rotate about this axis. Is anything split? Positive, negative? No. So we don't have to do the square root of y and the square root of x. In fact, what variable do we need? We don't even need the y variable anymore, do we? We need the x variable. Look at your function. you have y equals x squared. That's what we need, is it not? Yes. Okay. So, anyway, if you're rotating it about, all this stuff's messing. X equals 2. If you're rotating about, going from there to here, okay, going from rotating about x equals 2, going this way about x equals 2. Remember, for your radius, you're going to be right minus left. But for your function, what are you going to do? Top minus bottom. What is the top function? 4 minus the bottom function, which is your parabola, which is going to be what? Top minus bottom. Okay, D. I'm going to let you do D. Okay, so you have 2 pi. And boundaries are going to be negative 2 to 2. But this time, what is it? X equals negative 3. It's here. So, for your radius, it's right minus left. So what's it going to be? X minus a negative 3 or x plus 3, however you want to. I'm going to write it as x minus a negative 3 so that you'll see it. Right minus left. So this time it's your radius minus your shift because it's right minus left. Now let's go with the function. What's the function going to be? Stays the same. And again, if you write x plus 3, that's fine. However you want to do it. So what do you think?
Just so I'm clear, the 2 and negative 2 boundaries come from solving y equals x squared or x and using 4.
You can do it that way. Yes. Yes, if you're ever questioning about your boundaries, use some algebra. Okay? Now, that is your test next week. And again, no, we'll skip 6.4. 6.4 is just I'm sure when I tell you this, you're really going to want to do it.